So today we're going to be doing something called numerical integration. This is basically, this isn't going to be too important in what follows, but I think it's good for you to see it. Okay, so the point is that there are some functions don't have elementary antiderivatives. Some functions don't have elementary antiderivatives, right? You're trying to evaluate an integral. You've got your main tool, at least in the calculus class, your main tool is the fundamental theorem of calculus. So, if you have an antiderivative, you can evaluate it at the endpoints, and that's the end. But what happens if you don't have an antiderivative? How do you get the definite integral? How do you get a definite integral? Right? E to the, for example, e to the x squared, doesn't have any elementary antiderivative. Now, we did from the first fundamental theorem of calculus. You can always write down an antiderivative, right? You can always write down that area guy. The integral from 0 to x of e to the negative t squared dt, right? But this is just a sort of theoretically useful thing, right? This doesn't give you, if I want the definite integral of this function from 0 to 1, I can't use this, right? Because it would involve evaluating the definite integral, right? So it's you wouldn't be able to use this in a fundamental theorem of calculus. It wouldn't be helpful. Okay, so how do you get the definite integral? There are a couple of approximations. So here's a sort of simple idea, and that is that if you have a function from a to b, a function over ab, then partition AB into n equal parts. Right. Partition AB into n equal parts, and then so you split the interval into n parts. Okay, and then you take a what's called a piecewise linear approximation of the function. Right. So what happens is you take at each interval, take the endpoint and evaluate the function there. Okay. And then you just draw straight lines. So you make a piecewise linear approximation, right? So, take a piecewise linear approximation, right? And then take the integral of that, right? And then use the approximations. Use the approximations definite integral as an approximation of the function's integral. And so this is called the trapezoidal approximation. Trapezoidal approximation. So right, this is just a variation on, it's sort of a variation on how you calculate, how theoretically we define the definite integral. Right? You remember how we defined the definite integral? We said one way was to take a partition and then take, you could take, say, the right endpoints and then make approximation like this, right? This is called, I don't know if you saw this when you were in Calc 1, but this is one way of getting to the definite integral. You have this thing called the right endpoint approximation, where you divide the base into n parts. You take the right endpoint as your height, right, and you use that thing to approximate the area, right? You use that thing to approximate the area, right? This is called the right endpoint approximation, right? Endpoint approximation. Okay. And you can see that maybe trapezoidal approximation might give you something a little bit better than the right endpoint approximation, right? Okay. So let's call these values. Let's call this first height y0, the second height y1, etc., up to yn. Okay, so this point is yn. Okay, so let me draw it again. So suppose I have A, B. Just going to make a few points. Okay, so let's call this thing x0, x1, x2, x3, x4, x5, right? And their heights y0, y1, y2, y3, y4, y5. Okay. So the coordinates of each point are x0, y0, x1, y1, dot, 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 x5, y5, right? X, y, y5. Just notation. Okay, so what's the approximation? What's the area? What's the area under the trapezoidal? What's the area under the trapezoidal approximation? See if you can come up with a formula for it. Take a minute and come up with a formula. Should be pretty straightforward. You just need to know the area of the trapezoid. Okay, turn to somebody and talk to them, please. I'm hoping that that was pretty easy. Somebody tell me what you get. For example, what's the area of this first trapezoid? Hannah, please.
y0 plus y1 times the width divided by 2.
Yes. Okay. So y0 plus y1 over 2 times the width, which is b minus a over n, or 5, I guess. Right. Why does that make sense? Well, because you take the average height, right? You take the average height from here to here. The height here is y0. The height here is y1, right? This height is y0. This height is y1. And so what's the area? Well, it's going to be the average height, y0 plus y1 over 2, times the width of the base, which is b minus a over n. Mr. Al?
Is that necessary for the partitions to be equal?
Yes. Yes. So I'm sorry. Yeah, I should have said that. Yeah. So the partitions, we take b minus a and divide it into n parts. Yeah, all the same. Okay. Right. And so then you would do, you get y1 plus y2 over 2 times the same thing, right? Et cetera, right? So in the end, what you're going to get is, let me write it like this, b minus a over n divided by 2 times y0 plus 2y1 plus 2y2 plus 2yn minus 1 plus yn. Because I get yn minus 1 plus y sub n over 2 times b minus a over. Let me make this n instead of 5, just to make it general. Right? You get y0 plus y1 over 2, y1 plus y2 over 2, dot, 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 yn plus yn minus 1 plus yn over 2. Right? You factor out the common terms, right? The b minus a over n, you factor out the 1/2, you factor out, right? And then you've got y0 plus y1 plus y1 plus y2 plus y2, right? You get y0 plus 2y1s, 2y2s, dot, 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 2yn minus 1s, and 1y sub n. Okay. So this, we could have shown you in elementary school, right? This is called the nth trapezoidal approximation. Nth trapezoidal approximation of the definite integral. Okay, and we're denoting it by t sub n. Everybody all right? Pretty simple, right? Again, this is something you could have done as a kid. Okay. So if somebody wants you to give an approximation of some function, all you need to do is just divide this into n points. However many points. So suppose they say I want the 10th trapezoidal approximation of some function. You just divide your base into 10 points, evaluate, and then plug in values. Okay, so it's nothing fancy. Okay, so that's not particularly interesting. The interesting part, here is the interesting part. Can we give a bound on the error? Can we give a bound on the error? That is, can we control the error? Can we give some number and say the error is smaller than this number, right? Really, we call this thing an upper bound. Upper bound. Right? It's just some control on it. Okay. Like how big can the error be? How big can the error be? For that, we have a theorem that I'm afraid we're not going to explain, but here it is. Suppose f double prime is continuous on AB. Okay. Then, no. Suppose f double prime is continuous on AB, and there's some number m, and there's an m such that the absolute value of that second derivative is controlled by, is smaller than m. Okay. In other words, you have a bound on the second derivative. Okay. Suppose your second derivative is continuous, and you know some number that's bigger than the absolute value of the second derivative. Then the error, the difference between the definite integral and the nth trapezoidal approximation is smaller than b minus a cubed times m over 12n squared. Let me give you an example of how you would use this theorem, and maybe that will make it clear what this theorem means. Okay, so here's an example. Somebody asks you for the definite integral between 0 and pi of x sine x. Okay, and for some reason you've forgotten all your calculus knowledge. I know you can integrate this, but let's just use this as an example. Okay, so somebody says, use the trapezoidal approximation. How bad is the error? So you'd say, well, right, this is my function here. F of x is x sine x, right? F double prime x is 2 cosine x minus x sine x. Okay. Okay. And the theorem says, if we can get some sort of upper bound on f double prime, then we can get control on how bad the nth approximation is. Okay. So let's find an m such that f double prime is less than m on 0 pi. Okay. Once we get that, then we'll have some control on our error. Okay. Okay, so I'm going to get the control again in a very crude way. So again, I know you can probably get a better control than what I'm about to do, but I'm going to do it this way anyway, just to show you how one way to do it. Okay, you say, okay, well, let's think. Well, if I look at the absolute value of x double prime, that's the absolute value of 2 cosine x minus x sine x. Sure, right? That's what it is. Okay. I just want some number that's bigger than this on my 0 pi interval. Okay, so I'm going to do something really coarse, which is I'm going to say, well, I know that this is smaller than 2 cosine x plus absolute value of x sine x. Okay? It's a really crude thing to do, but I'm going to do it. Okay. So I'm using what's called the triangle inequality. Triangle inequality. Right? That says if you have the absolute value of the sum, it's less than or equal to the sum of the absolute values. Absolute value of a sum is less than or equal to the sum of the absolute values. So here I've got this sum. I'm saying, well, that's less than or equal to the absolute value of this guy plus the absolute value of that guy. Okay. Okay. And then I'm going to say, okay, well, I can pull the 2 out, right? Let me pull this 2 out up here. No, I'll pull it down here. So this is the same thing as 2 times the absolute value of cosine x plus the absolute value of x times the absolute value of sine x. Right? Because the absolute value of a product is the same as the product of the absolute values. Okay. Okay. And now I'm going to say, well, look, on 0 pi, I know that the cosine is always smaller than 1. So this is less than or equal to 2 times 1. X, the biggest that x could be is pi, right? So the absolute value of x is always going to be less than or equal to pi, and the absolute value of sine x is less than or equal to 1. So in the end, I get 2 plus pi. So getting an upper bound for the absolute value of f of x on my interval AB. Right. This is the m. This is the m that we're gonna use. Okay, is everybody all right with how we got that? I know you could have gotten in some better way, right? You could have taken the derivative of this and looked for the maximum and the minimum, and then you've gotten a very good bound. But we don't need a very good bound. We just need some bound. Okay, we don't need the best bound. We just need any bound. Okay. And here's one that'll do it. 2 plus pi. I mean, now that I know it's 2 plus pi, I could say let my m be 10. That's also fine, right? We just need some number that's bigger than the absolute value of the second derivative. Okay. Is everybody okay with how we got it, even if you're not sure what we're going to do with it? Okay. So we're wondering, right? What's the control on the error? Well, so our theorem says. So, using P sub n to approximate see that, you calculate m equals 2 plus pi will do. Okay, and then our theorem says that the error, the difference between the integral and our trapezoidal approximation is controlled by b minus a, that's pi, right? B minus a over, b minus a cubed over 12n squared times m. Okay. So this tells you that the nth trapezoidal approximation is at most this wrong. This is how wrong it is, at most. Okay. So, right, if we take the 10th, if we take t sub 10, right, if we take the 10th trapezoidal approximation, we know that the error is smaller than pi cubed 2 plus pi over 12 times 1 over 100. Okay, if we take the 100th approximation, we know that it's this number times 1 over 100 squared, right? 1 over 10,000, right? And so this tells you how bad your trapezoidal approximation is. Okay. Okay. Everybody getting the idea of what we're trying to do here? Yes, Catherine.
What is the word before or after theorem says?
Theorem says error, the error, this is the error. The error is less than or equal to this. Okay, so right. So if somebody said, I want you to give me the actual integral up to 0.1, right? They said, I want you to give me the actual integral, and it cannot be more than 0.1 wrong, right? Cannot be more than 0.1 wrong. You can say, okay, well, I just have to choose my n big enough that this thing is smaller than 0.1. Right? Everybody understand that? Right? If the error must be smaller than some number, 0.1, say, just choose n such that this thing is smaller than 0.1, right? So it tells you how far out you have to go, right? You can figure out what approximation you need in order to get that accuracy. Okay, that's the point of this formula, right? It tells you how far out, what approximation you need to take in order to get that accuracy. Okay, any questions? Any questions? Yes, Mira.
What is the SU? Just she was like
Such that, sorry,
Okay.
such that. Sort of like so that. You choose the n so that this thing is smaller than 0.1. Let's see.
Can you explain the last line?
This last line here?
Yeah.
This one or this one? This one? This one.
Is it the same line?
It is the same line. I mean, so if we take the 10th approximation, then the error will be smaller than. Right, so the error is smaller than this thing right here, right? Where n is the approximation that you take. Okay. If we take the 10th approximation, then n is 10, right? So we get 1 over 100, right? If we take the 100th approximation, the error is, this thing. The error is smaller than this thing times 1 over 10,000, right? If we take the 1,000th approximation, et cetera, et cetera. Okay. Let me go on to the next, the second method. There's another method called the parabolic approximation. Okay. So similar idea. Right? You have some function. You want to take its definite integral, but you don't have the antiderivative. And the idea is divide AB into an even number of pieces. Okay, into n pieces, but n has to be an even number. N will be an even number this time. Okay. Then on every 2 subintervals, approximate with parabolas. Okay. So, right, so, okay, so you'd say, okay, I take the first, you take these 3 points. Okay. You take the first 2 subintervals, and you take these 3 points, and you would approximate that with some parabola. Okay, by some parabola that passes through those 3 points. Okay. Then you move to the next pair of intervals. And you'd say, okay, I'm going to approximate that with a parabola, right? Then you take the next subinterval, and you say, okay, I'm going to approximate that thing with a parabola. And you keep on going. Okay. Okay. The point is that, previously we did it with just one interval. 2 points determine a line, 3 points determine a parabola. 3 points determine a parabola. Okay, so just as 2 points determine a line, 3 points determine a parabola. Okay, and so then what you do is you find the integrals under these quadratic regions. Okay, you find the integrals under these quadratic regions. So as an exercise, if you have if you have 3 points of height y0, y1, and y2, and you have a parabola going through them, then the area turns out to be h over 3 times y0 plus 4y1 plus y2. So our formula is going to be the parabolic approximation of the integral will be h over 3 times, again, if we call these points y0, y1, y2, etc., it's going to be h over 3 y0 plus 4y1 plus 2y2 plus 4y3 plus 2y4 plus plus 2y n minus 2 plus 4y n minus 1 plus y n. Does that make sense? Does it make sense? Right? On each parabola, right? So from here to here, y0, y1, y2. Sorry, people are still copying. Does that make sense? So the area under this first parabola, right, is going to be the area of this first region here is going to be h over 3 times y0 plus 4y1 plus y2, right? For the second region, it's going to be h over 3 times y2 plus 4y3 plus y4, right? And so on and so forth. And so you see you're going to get y0 plus 4y1 plus 2y2, right? Plus 4y3 plus 2y4, et cetera, et cetera. So you get 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 1, right? 4, 1, 2, 4, 1, right? Okay, so that will be the, that's the formula for the parabolic approximation. Okay, I'm sorry, I should probably close up class. Yes, Jessica.
Can you explain why it's 4?
So that's from this thing, this exercise. So maybe we'll go over this at the beginning of class next time. I think I got too fast.